In my previous video, I gave you an example of how to deal with torque and what that looks like in real life. Now let's talk about some definitions. When we did linear dynamics and we wanted to talk about changing the velocity of an object, we dealt with forces, pushes or pulls. If there was a net force acting on an object, that would change the velocity of the object and we would get acceleration. But when we talk about rotation, there's a few more things that need to be taken into account. If we have an object that is going to rotate either more or less, there needs to be a net torque. And as I showed you in the previous video, not only is the force important, but where that force is applied is going to be important. And those combine together to give us the concept of torque. The symbol for torque is going to be the Greek letter tau. As we're going to discuss in a moment, the units for that, based on the formula, end up being meter newtons. Meters are going to come from where that force is applied. Newtons are obviously coming from force. However, there's one more thing that is also going to affect how much torque is present. So to be perfectly clear, let's talk about those three effects one more time. First of all, amount of force. How much push or pull is coming from some external effect. So in the case of me pushing the door, the force that my hand applied to the door is going to be the force. But we could get forces from friction, we can get forces from tension, we can get forces from normal forces, gravity can cause things to rotate. All of the forces that we've talked about in the past might be putting a force on an object and causing it to rotate about an axis. The second thing we're going to look at is how far that force is applied in that distance between the axis of rotation or the fulcrum of the object all the way to the point of application of the force. This is another case where we are going to use a lowercase letter r to represent that vector distance. You will also sometimes hear this referred to as the moment arm. The final thing we're going to look at is the angle between the vector for the moment arm, r, and the force vector, and that will be measured and given to you with the symbol theta. Let's do some examples here of what that looks like based on my door. So if we think of what I was doing with the door in the first video, I initially took my finger and pushed on the door very close to the hinge. The hinge is where the axis of rotation was for the door. If we were going to add in what I've called the moment arm, or the distance from the axis of rotation to the force, what we're going to do is I'll draw a little point at the axis of rotation, and my vector is going to be touching the point where I applied that force. So this little vector, red vector here, is going to represent my moment arm, or R. Now, in the second situation, I came over to the other end of the door and I applied my force here. And as I mentioned, I was actually able to make my force smaller, if Notability would agree with me here. So. but I actually got a bigger acceleration, angular acceleration of the door, because I was pushing much further away from the axis of rotation. So in this case, we have a very large R value, or moment arm, which provides for a much larger torque. Now, as I mentioned in the previous slide, the angle at which you apply that force is going to be important as well. And this might make sense to you, because if you think of me taking my force and instead of pushing on the door, I were to pull on the door like this, you would say, well, that's ridiculous, Mr. Schramm, because the door is not going to rotate if you pull on it like that. And our formula is going to say, yeah, you're not going to get any torque if you do something like that. And in fact, our formula is going to say, if you push on a door like this, you're actually going to get the maximum amount of torque possible based on the angle. But if you think about going through a door sometimes, as the door rotates, if you keep walking forward while you push the door, but you keep your arm straight, you might not be pushing on the door at quite the same angle that you were before. And this is actually going to affect how much torque you're getting, and you're not going to get as much angular acceleration as you were before because of the angle of that force. So this is just getting at the idea that the angle is going to be important. Now, to measure that angle, it's a little bit trickier to think about. What we need to do is, we had that R value, and then we had the force value, and if I copied those from the picture below, or above, sorry, we would have had something like this. Unfortunately, this is not how you determine the angle between R and F. To find the angle between R and F, you actually have to move them so that they are touching tail to tail, and now you look at the angle between them. And in this case, you get an angle of 90 degrees, which ends up producing maximum torque. If we go to that ridiculous situation where I was pulling away from the hinges, like this, now the angle between the two vectors is 0 degrees, and we get no torque in this particular case. So luckily, in most cases in AP Physics 1, the angle between R and F is going to be 90 degrees, and so you don't really need to worry about it too much, okay? But of course, there will be situations where sometimes they give you an angle between the two, and you need to be able to figure out where the angle is and determine how much torque you get when you don't have a 90-degree angle or a 0-degree angle between the two vectors. All right, so what does this formula end up being? Well, first part's easy. So you need to be able to calculate torque. So torque is going to be equal to the combination of these variables. The easy ones are R and F, okay? And what you want to do is take the two parts of those vectors that are perpendicular to each other. And so you will see on your formula sheet that they put these two things together. Now, if R and F are at a 90-degree angle to each other, life is good. You just take the R value and you multiply by the F value and you get the torque. But if you get an angle that's not 90 degrees, what that means is that you have to take that angle into account, and r perpendicular to f, finding the angle, the perpendicular parts of those vectors to each other, basically boils down to doing r times f times the sine of the angle between the two vectors. And so if you do sine of 90 degrees, you get 1, which maximizes r times f. If r and f are parallel to each other, or in other words, if you are pulling on that door away from the hinges in a silly sort of way, well, now your angle is 0, and sine of 0 is 0, and that tells you you're getting no torque in that situation. It doesn't matter in this case if you choose to use the radian system or the degree system to measure your angle. You're just plugging into the sine of the angle formula to determine whether or not there is torque in the situation or not. So just make sure whatever angle system you are using matches whatever angle system is in your calculator. Or in other words, if you are choosing to measure that angle in degrees, make sure your calculator isn't in radian mode when you go and calculate the torque if you have to deal with an angle that's not 90 degrees. So that's how we're going to calculate torques. They're related to forces. The analogous idea, I guess, is related to forces when we did linear motion. The tricky part is we just have to do a little bit more. Instead of just giving you an amount of force, well, now you have to do an extra step dealing with where that force is applied and the amount of force and the angle to determine the amount of torque.